I'm going to take a look at the calendar real quick. Let's see. First of all, if you have any trouble switching to the HTML version, apparently some trouble switching to HTML version in the WebCT. Okay. If you have any trouble with that, I guess for future assignments, if it looks like you're going to have trouble, try doing it in a Word document and attaching it, or in a PDF, or even Notepad. Just anything that will maintain the breaks between. But if worst comes to worst and you submit it and the formatting is gone, I'll decipher it. So, a couple things before we get started. We're going to finish up some of the rest of Chapter 6 today. We are spending a little bit longer on Chapter 6, which I don't mind because it is an important chapter. It's probably this, the next chapter, and then obviously the chapter we did before. They're all kind of tightly related, so understanding this aspect is very important. This is probably going to be one of the central aspects of the midterm, okay? Because obviously 3 whole chapters on this specific topic of multiple processors doing things at once is very important. And on that topic, on the calendar, we have the last day to withdraw is the 6th, okay, right here. So these are going to be bumped down to the next week. I'm going to shift everything down. And then we're probably going to do the midterm on Tuesday. Okay? And then go over, and then we can kind of go over some of it on Thursday. Okay? The midterm will not include Chapter 8. Okay, and I'll put a post up in the discussion board on this. We're going to start Chapter 8 that week before. We're probably going to take this day to do more review. We're going to do review over what's going to be on the midterm and on the subject matter we've covered already. And then, so that way, when we come back from the midterm, we can finish up with that memory management and then continue into virtual memory. Okay, because those are kind of related. So the midterm will mostly cover, the main content chapters that we saw. Okay, Chapter 1 is the introduction, and I will have a little bit of discussion on the kind of overview concepts we saw in Chapter 1, like kind of the responsibilities of an operating system, kind of what its purpose is. Some of that discussion that we saw in the first week about. We've talked a lot about the operating system being responsible for resource management, sharing of resources between users, and what kind of benefits we can get there. We saw some questions in our homework about things like, time-shared versus exclusive access machines, that kind of thing. Okay. Obviously, the more kind of meatier content was found from Chapter 3, and then these chapters we're going over on multi-threading 5 through 7. Okay, so again, on the 28th, I'll go in more detail and review over what kind of things you can expect. But keep in mind that this area is the main, kind of content areas. These 3 weeks are the main content area that we've covered for before the midterm. So obviously concentrate a lot of your studying on that. Okay. My test usually, if you see me covering it a lot and going into detail in class, it's going to be on the test. So one thing we've obviously seen on that is like this idea of how to solve this mutual exclusion problem. We spent a lot of time on that algorithm that we saw, that Peterson's solution to the mutual exclusion problem. Okay, we concentrate a lot on that the interleaving of those instructions when we were looking at counter, the counter variable between a producer and consumer. Okay, so obviously those are going to be very important. The CPU scheduling, we did a lot on the the scheduling algorithms, seeing how processes, what order they'd end up executing in, depending on the algorithm. So that's obviously very important. Okay, again on the 28th we'll go in more detail over the specific topics that are going to be on the midterm and what you should be studying. But obviously getting a head start and knowing which parts to concentrate on in the chapter can help out. What's that? The midterm is going to be, I'll put it on the, it's the 3rd, yeah. The Tuesday before the last day of the withdrawal, so the 3rd. Okay. These are going to be bumped down. So I'll rearrange the calendar on WebCT so you can see where the midterm is. And I will probably go ahead and, on the calendar, and split this day to show that we're going to talk a little bit about the chapter at the beginning and then review for the midterm afterwards. And then we're kind of going to finish that chapter on Thursday, and then I'm going to take some of the class to review the midterm. Okay? Because my goal is to give you the midterm on Tuesday, get it back to you on Thursday, so you can see where you stand and that kind of thing before the last drop date. And everybody needs to do well because we can't afford to have anybody drop. There's very few people here. So, huh?
Make this easy. Yeah.
Simple.
Let's just say I believe in all of you.
I have a question.
Yeah.
Do you have any like sample test or if you have taken previous to this course?
No. If you see any of like the other classes I teach, my tests are very challenging. They're very challenging, but I'm very fair about my tests. I don't usually go to a curve unless I need to, but I do look at the whole class, at how they answer questions to kind of determine, how strictly I should count points on a particular question. So I kind of do a mini curve on every question. I kind of look at how people answered a question, and then I try to gauge which of it's my fault and which of it is all of your fault. Right? I try and gauge how people heard the material. So if you feel clear on what we go over in class and you're asking questions about things that are unclear, I obviously try to design my tests to give people A's who understand and lower grades if people are obviously not paying attention on various or particular aspects. Okay. A lot of the questions are going to be in the style of the assignments. Okay. I am going to have a mix of kind of more open answer questions and then more kind of empirical questions that have a specific answer that there's no question, like the scheduling and things like that. And for this class, since we're so small, I'm going to do probably all essay instead of, there's not going to be multiple choice. And by essay, I mean like some of them will be like drawing little boxes showing when processes run and stuff like that. Kind of like what we saw in the homework. Okay. But yeah, I think I give good tests. So, like I said, they're very challenging, but my goal in them being challenging is not to count off a bunch of points for everybody. My goal in being challenging is to surpass what you know so I can see, where you are as far as the question goes. So even though you might not completely understand, and get the exact right answer for a question, you will probably still get all the points if you demonstrate a level of knowledge on the topic, on the subject. Okay. Yeah, I think tests should kind of do that. They should push to the edge, just beyond what your knowledge is, so you can see exactly where there's a nice contrast between what you know and what you don't know. So I can see where that line is and see if that line is, A high or or a low grade.
I tried to listen to your lecture.
I had to take. I exceeded my my disk space on Techie, so I have to move to another server. What I might do is I might put them on Google Video, and then just link to Google Video. So they're turning out to be very big, so I have to find another easy way to store them. So they're about I don't know, they're about 200 meg a class. So for a week that's 400 meg, and I'm a gig after 2 weeks. So it's pretty expensive. And I easily exceeded my disk quota on Techie on on the computer science web server. I easily exceeded my quota. So I'm gonna probably put them on Google Video and then link off that same page that I gave everybody. Okay. So let's get started. Okay. We are still looking at some concepts in, what is it, chapter 6, I believe? Yeah, chapter 6. Okay, but we've gotten through kind of the major we're way back. Okay. So we stopped around here. Okay. Last week, what we went over, okay, I really, really concentrated on that fundamental problem of why we need this mutual exclusion, in the problems the basic problem we saw with producer-consumer, okay. The kind of fundamental way that we solve the problem by getting smaller operations that we can do without interruption and kind of extending them so that we can cover a larger section of code, right? So we could not prevent these interruptions for the producer-consumer problem, but we could prevent it with that very small part of the Peterson solution, right, of that algorithm we saw, okay? So what we did was we used the algorithm to make it so that we could make a longer section like the producer-consumer problem locked. In other words, so that they can't jump between them in a way that gives us incorrect answers. Okay? So what we do is we take that basic concept and we extend it to more kind of general purpose tools. Okay? And then when we get these general purpose tools, we can do very complex multi-threaded or multi-process programming. Okay? So I initially showed you this construct here, the semaphore. Okay, so the semaphore is kind of one of the very basic tools that we use for synchronizing two processes. Okay, and we saw that there's two operations: wait and signal. Okay, so we can do the algorithm we saw for synchronization using these if we wish. Okay? In other words, the more complex code of this algorithm can be simplified by just using semaphores. Okay? What we do is we just lock, right, or wait, use the wait call before a critical section, and then after a critical section we do a signal. Okay? And if somebody else uses a wait and signal on the same semaphore, okay, then we have mutual exclusion. Okay? So, we learned that the semaphore, okay, they're used in one basic way, okay, but making a semaphore only take on two values, 0 and 1, okay, they're often called a binary semaphore. Okay? And those are also called mutex locks. Okay? So when you see this word, okay, this word up here, mutex, okay, that's just another word for a semaphore that takes on 0 and 1. Okay? But we've also seen that a semaphore can take on any number as well. Okay? And we can use that for having multiple processes waiting for kind of different copies of the same resource. Okay? So if I have a lot that can go up to 5, for example, okay, that's saying that 5 processes can get this semaphore, and then the 6th process has to wait. And then as those processes release their semaphore, right, then additional processes can get at that resource. So in other words, you can have up to 5 processes at the same time using this resource. Questions on that? Okay, that's a little bit more of an advanced feature that we didn't see with the basic algorithm, the basic Peterson algorithm.
Is this the same one you said last time that somebody go online and finish the ticket?
Yeah, the tickets, right. There's tickets in a bucket, and you can give out 5 tickets, and when you get done, you put a ticket back in the bucket. Okay, so this is a more advanced synchronization method. Okay, so we saw that the implementation, okay, for the wait and signal operations, we need to make sure that those don't conflict with other processes. Okay, so we have a couple options as to how we implement wait and signal at the operating system level. Okay, the first one, okay, that I mentioned was very well suited to single processors. Okay, that is, you have 2 processes, right, running on one processor. Okay. What's the best way to make sure that the other process can't break the signal or wait call of the other process? Where does the problem come in with this synchronization when multiple processes are running? Interrupts, right? One of them gets interrupted in the middle of what it's doing, and then the other one comes in, and then a problem comes in if it starts modifying variables from the other process that they share together, right? So, what's an easy way to prevent that from happening? Okay, you can disable interrupts. So if you disable interrupts while you're doing wait or signal, you make it so that neither one will stop the other. Okay? Now, given that we're disabling interrupts, okay, we saw that this one. What do we notice in wait that happens with the waiting process? What does it do in here? What does this code say? While s less than or equal to 0, what do we do? So what does that mean? We loop, right? We keep checking that condition. And then we can finally decrement. Okay? What's the problem with this? What's that? Right. I mean, it could be infinite if that doesn't happen, but we need it to be infinite if that doesn't happen, right? We need it to stay there. But What's the problem with that? One of the processes is executing this loop, right? So it's using the processor to do what? To do nothing, right? The processor has to execute these commands of looping and checking the condition over and over and over. Okay? This is called busy waiting. Okay? Busy waiting is the processor executing instructions to do nothing. Okay? Busy waiting, all the time that a process is busy waiting is CPU time that another process could be using to do work. Okay? So, given that, we can switch to a different implementation on a single processor machine that does not do busy waiting. Okay? Instead, it uses signaling to have the other process wait. Okay? So, when a process, we need two other operations. One is block and one is wake up. These operations are simply block means put a process into the wait state. Wake up means take that process and put it back into the ready state. Does everybody remember the state diagram we saw in the chapter on processes? Okay? That state diagram had a number of states that individual processes could be in. Okay? There was running, right? There was ready, and there was wait. Those were three of the major ones. Okay? Well, when you're in wait, you're not eligible to be put in the queue, right? To be put on the processor. That's good because all the other ones that are ready can be running on the CPU, right? So what we do is we block, put it into the wait queue, right? And then when we're ready for it again, we wake it up, put it into the ready queue. The ready queue will eventually use the scheduler to put it on the CPU again. So how do we implement this? How do we implement the semaphores now? Well, now we do block instead of that while loop. Okay? Because this block is saying, sit in the wait state until I signal you. So in other words, that's as long a wait as you want. And it's not using any CPU. Okay? When the other process signals the semaphore, okay, it will send the wake up signal. And we've seen that we can use signals to move those processes back into the ready queue. We saw this with things like disk access and other input-output, right? When a process wanted to do input-output, it was put into the wait state, and then when the disk or whatever was done, it signaled, and then it popped back in the ready queue. Okay? This is more efficient for single processor systems because now, when a process is waiting for a semaphore, it's actually taken off the queue. Okay, so it's not rotated in. Questions on that?
Yeah. This is probably like primitive idea, but my question, I was reading and get confused there that there is a wait and continuous loop. And it's the CPU is wasting time. Okay. My question is, the process is waiting. Isn't it that time another process is actually running there? That's why it's waiting.
Well, all processes have to wait if another process is running. Okay?
Right.
That's always going to happen. Being in the wait state is different from being in the interrupted state. In other words, you're running, and then the processor stopped you, put another process on, ran it for a little bit, stopped it, put another process on. You're in the running state the whole time there, right? Being in the wait state is different. Being in the wait state means that if I'm the CPU scheduler and I'm sitting there giving processes some of the CPU time, I'm not even going to look at you. I'm not even going to put you onto the processor because you're in the wait state. I know you're not doing anything.
But that could cause a starvation. But my question is that, if it says the CPU is wasting them, that's where...
That doesn't necessarily cause a starvation, but go ahead.
But, that's where I get confused. Like, why a CPU going to be wasting time? It's just a wait state. If it's continuously making a loop and wait...
That's not the wait state. Doing a loop is not the wait state. Right? Doing a loop is executing instructions. right? You have while loops in all your programs. You can't just consider a while loop waiting. You see what I'm saying? A while loop is a sequence of instructions when you look at them on the machine. It's check a condition, right? See if the condition, jump not zero, you go back, right? And you jump not zero out of the loop, jump if zero back to the beginning loop. Those are instructions that the CPU has to calculate. That's not waiting. That's actually doing instructions. We call it waiting because the process isn't doing anything. The program isn't doing anything useful. You see how doing a while loop is different from waiting?
Right. I was different.
Well, that's all you. I mean, that's all that needs. What did the book say? The book said the same thing. That a while loop is called busy waiting in the sense that, and they make the distinction between waiting and busy waiting. Because busy waiting is using CPU cycles. Waiting, not using CPU cycles. That's the difference. That's the only difference. In fact, these perform the same. The difference is the busy waiting needs the CPU to execute instructions to wait. Okay. No, I mean it's the same. That's the thing that needs to be clear, is that they are the same. This is from the book, and what I'm saying is, the same idea that's in the book. I mean, if you're saying that the book is saying something about waiting,
spinning lock part, that part is what
that's the only distinction we need to make here. Is everybody needs to be clear on what spin lock is, on what spin lock or busy waiting is, and what this is. This is the opposite of spin lock. Okay? So let's take a quick look here. Spin lock. Okay? Okay, so you have two processes that are running, right? You have P0 and P1. Okay? They're both running. Okay? And we get to a point where they want to lock each other out. Okay? So there is a critical section here and a critical section here. Okay? We're going to use locks. We're going to use a mutex lock, okay, which is nothing more than a semaphore, which can take a 0 or a 1. Okay? So, what calls do we put around the critical section? What calls do we put around the critical section? What do we have to put here to make sure that these critical... By critical section, what do I mean by that?
Like only one
one process, not processor. One process
can update that and other
can be running the critical section at a time. In other words, if P0 is running this critical section, P1 cannot be running its critical section, and vice versa. So, what do we put in here? I'll give you a lock. Okay, I'll give you a lock. It's called lock. That's shared between the two. So, what do we do? What do you mean put the lock?
Lock to the process 1.
Process 1?
Yeah.
Okay, so by lock to process 1, what do you mean? Semaphore does not have a call called lock. Wait. Lock.
So process 0 can go to the critical section.
Okay, so is that all we need?
Now once you finish, then it unlock the.
So this needs to unlock.
Unlock the signal.
Is that enough?
Update the 0 or 1, which is actually signal. So.
Well, if I'm going to do this, okay, this does one thing. Okay, this is actually a way. This pattern makes sure that P0's critical section runs before P1's critical section. And you'd have to initialize lock to zero. In other words, locked. Okay? Because you're going to unlock it here, and then this guy can lock it. Okay? This will always run like this, in this pattern. P0, then P1. We weren't trying to do that. We're trying to run them at the same time. So what do? Wait signal again. So we go wait and signal. And we start lock off at 1. Unlock. Whoever gets here first will lock, run their critical section, unlock, and then the other one will probably be waiting there already and be able to run its critical section. Okay, so that's the semaphore to make it so that they're mutually exclusive. Okay, now here's where we run into this idea between spin locks and just waiting. Okay, spin locks are busy waiting, and then there's regular waiting. So if I'm the CPU, okay, I'm scheduling P0 and P1. Before all this, I'm just running a little bit here, running a little bit here. Chances are I have a bunch of other processes running too. So I'll run a little bit here, a little bit here, a little bit through all these. Okay? So when I get to here, okay, I run a little bit of P0. I call wait lock. It's unlocked. So I lock it. I start running my critical section. I interrupt. And now it's P1's turn, as usual. Okay? I get to here. What will happen? I'll try to lock, right? And what will I notice? It's locked. Right? It's locked. So what do I have to do? I have to wait. Okay? Now, here's the difference. If we're spin locking, busy waiting, what does the code inside wait look like? It looks like a while, and then an empty while loop. Okay. So when I call wait, and I notice that it's locked, what am I going to do with my slice, my time slice? I'm going to run the while loop with the CPU. Okay? Then I'm going to get interrupted. Then where am I going to go? Run through the rest of my queue. Run a little bit here, run a little bit here, a little bit here, and then come back. Maybe run a little more in my critical section, get interrupted. Come here. I'm going to sit there and run that while loop for my time slice. How much of the time slice am I going to use? Huh? How much of my time slice? If I have a 10 quanta time slice, I'm going to use 10 quanta and get interrupted. If I have a 100 quanta time slice, how much of it am I going to use? All 100, right? Get interrupted, stop. Run through. I finally get here, I unlock, time slice. Come here, my while loop's going to terminate because I notice that it's unlocked. I'm going to lock it, run through, okay? That is spin locking. Busy waiting, okay? Now, let's go back. We're going to do this style, okay? Run, back to 1. So, I reset the programs, run again. Time slice, time slice, time slice, time slice, time slice, right? And I just run through all the processes. I come back, and I get to here. What do? I try to lock. Can I lock? Yeah, no problem. Right? Because I went to wait, and I was able to decrement it, and no problem. Okay? So, I start running my critical section, and I get interrupted. I come here. I'm running down, and I get to wait. What do? Decrement, Value is less than 0 now, right? We've decremented it to -1. What do? Block. Here's the difference. This process now goes to the wait state. Okay? I stop processing it immediately. I put it in the wait state.
Block to be -1.
Yes. Okay? I'm in the wait state. So what do? I stop running it, right? If I'm put in the wait queue instead of the ready queue or the running queue or running, I'm done with the CPU. CPU goes on, gets the next one in the ready queue, runs it a little.
What's the part of the quantum time is there? What can happen? Who's gonna get it?
What do you mean?
When you get the
When I switch to wait,
right,
the time quanta is done. Okay? Time quanta, right? The quantum is just for interrupting a process. If a process basically gives up the CPU, we'll take it. You don't have to finish the rest of the time slice.
Okay.
We stop. If we say, I'll gladly go onto the wait queue, we let him go on the wait queue and move on. Right? Okay? If we terminate, go on the wait queue, then we give up the CPU. Okay? So that's now waiting. Next time slice, next time slice, next time slice. Right? And we just go through all the other processes. Now when we come back here, we run through a little bit more. Time slice. Now what's different? After this time slice is interrupted, okay, we've exceeded our time slice, what do we do now? No. I said we time slice right here. We're still in the critical section. We time slice. Where do I go as the CPU? No. Go to P3. And I give it its time slice. And I go the next one its time slice. And the next one and the next one.
So they haven't had to wait or go to the wait queue?
These guys didn't.
Okay.
None of these guys, because they're not doing this locking.
Okay.
Right? These guys are just regular processes. I run some, run some, run some, run some. And then I get back here, and then let's say I get to the signal. What do I do now? Plus plus, value less than or equal to 0. By plus plus, 0, value is less than or equal to 0, I wake up this process from back here. Right? I wake up a process from the waiting queue. This guy. Switch him to ready. Right? Well, if I did that right here, and then now I get time sliced, right? I get interrupted. My next time slice, this guy is now eligible to run. So what will happen is he'll come here, he finished his block, and he just goes on. Runs through, interrupt, go through, come back, and now we're going. Okay? So the major difference between those two is that step where I skipped process 1 when doing the CPU schedule. Why couldn't I skip process 1 in the previous example? To do what? To process the while loop. Okay? So for every time that while loop was processing, with this mechanism, we get a free time slice that we could give to somebody else instead. So this is waiting. The other was busy waiting. Questions on that?
I got everything, but besides why did you get the -1? Because it was 1, that should be 0.
Well, that's a phenomena that happens in this mechanism. Okay, is that you actually do get negative values for that. what ends up happening is those negative values end up being how many people are waiting in this wait state. How many processes are waiting in this wait state. You didn't have that before because nobody was waiting in the wait state. They were all spin locking. You don't need to keep track of how many are waiting because the process itself is running and it keeps track of when it can go. Okay? But you don't see this. You don't see this value. You just know wait and signal. That's it. Okay? Because everything inside this, you don't need to know how it's implemented. In fact, you should prefer not to know, because if you're programming something that's using these waiting and signals, you don't want to try and understand what's inside the function, because if you do, your program might not run on a multiprocessor system, or it might not run on a uniprocessor system. If you need to know those details, you only know wait and signal. That's it. You know that wait will attempt to acquire the lock. If it can't acquire the lock, it will wait. And signal will signal an unlocking of the lock. And that's it. That's all you need to know. Okay? Us looking at operating systems, we, in the class, need to know what goes on in there because they're different. Okay? Okay? So typically, to implement this, we'll disable interrupts to make sure that nobody else can be modifying these values while we do it. Okay? Because again, this is targeted at uniprocessor systems. Okay? In multiprocessor systems, okay, where you have more than one thread running at the same time, more than one process running at the same time, okay, typically you will use spin locks. The reason being is that in multiple CPUs, if you wanted to do something like this, where you disable interrupts and then run this little piece of code to suspend processes, you'd have to disable interrupts on all your processors, which is usually not doable. Okay? So typically what will happen on multiprocessor systems is you will use spin locks, and on uniprocessor systems you can use these. Okay? These are more efficient in general because you are not doing busy waiting. Questions? No? So, deadlock we are going to talk about, it has its own chapter. Okay? Deadlocking is a phenomenon where two processes are waiting for each other. And they can't get to the point of signaling the other because they're waiting for the other one. Okay? It's a point where two different processes can't progress because they're dependent on each other. So, these three classical problems, that's going to be the last thing we really look at in this chapter. These are kind of archetypical problems that we look at to make to show that our different synchronization mechanisms work. Okay? Because these synchronization mechanisms are meant to solve these types of problems. Just like we saw the basic problem of producer-consumer. Okay? These are some more complex examples. Okay? The bounded buffer problem. Okay? N buffers, each can hold one item. Okay? And then we have a semaphore. Actually, just a regular lock. This is not a counting semaphore. Okay? It's a lock. Initialized to the value 1. Full initialized to 0. Okay? And empty initialized to n, which is the number of buffers you have. Okay? So those are the three locks we're going to use. So, this is the producer. Okay? It produces an item. Okay? It waits for an empty slot. Okay? Remember, we initialize this to n. In other words, all the slots are empty. Okay? This is basically saying, if there's an empty slot, I can proceed. And I get one. Wait mutex. Okay? Think of that as locking all the buffers so that we can write to it. Okay? We ran into a lot of problems with this mutual exclusion when people were when processes were trying to write to the same variables and whatnot. Okay? So we use this lock to make sure that only one process is fiddling with the buffer at a time. Okay? So we lock it. We do all our code for adding an item to the buffer, producing an item. We unlock it, and then what do? We increment this full semaphore. Okay? Full is the number of full buffers. Empty is the number of empty buffers. And then mutex is a lock. Oh. Okay, so the consumer. Wait full, what is that saying?
Fully wait, or full lock is full.
You guys are ready to go?
The simple way to say it is, if there's a full buffer, I can continue. In other words, wait for a full buffer. Okay? So, if there's a full buffer, in other words, a buffer with stuff in it, I can continue. So what do? I lock the buffers, because I'm going to manipulate them, and I take one out. And then I unlock the buffer, because I'm done manipulating it, and then I also say, hey, there's one more empty one, because I just emptied it. And then I continue. So just through the use of this basic idea of a semaphore, where we had two variations, one is 0 and 1, and one is any integer, right? A counting semaphore and a mutex, right? Using those two types, we created 3 semaphores, put them in this order, and now we have a buffered producer-consumer, right? The producer can keep producing stuff until it fills up all its buffers. The consumer will go to those buffers and pull items out. Okay? So that basic scenario that we said before when we were talking about processes talking to each other, where we have a buffer, the producer puts stuff on the table, and the consumer comes and picks them up, this is how we have to do it when we implement it, because it prevents these two different processes that are cooperating with each other from corrupting the shared buffer.
Suppose we didn't have, just suppose we didn't have the mutex, what would happen?
What would happen is there would be times when you're in the middle of removing an item from a buffer, and a producer might come and start writing into that area or something. Okay. You can get into situations where if you both have access to the buffer at the same time, you might be corrupting an item in the buffer that you're both trying to work with.
That comes the other way to the producer side.
It might
Mutex.
start trying to write into,
From producer side, if there was no mutex, so he was writing. At the same time,
the consumer's pulling one out. Well, I mean, they're both two different sides of the same problem, right? If you're trying to write while one's trying to, if you're trying to produce while one's trying to consume, there's a chance that you're both going to use the same area. If you're not using the same area, if you're, the producer is working in this buffer over here and the consumer is working in this buffer over here, you won't corrupt each other because you're not in the same space. But in that scenario, what could happen is the counter problem we saw before, where while you're updating the counter and I'm updating the counter, I'm trying to, as the consumer, I'm trying to decrement the counter. As a producer, I'm trying to increment the counter. If you get to that exact point at the same time, you could have an inconsistent count. So now your buffer doesn't reflect the count. So if you don't have those locks that we see here, you'll run into that initial problem that we saw before, where you both try to manipulate a variable, like the counter or individual items in the buffer. Questions? Okay. So this is a very classical problem of why we need these different tools. Readers and writers problem. Okay? This is a slight variation on what we saw in that we're still sharing items between two different processes. Okay? The trick is that there are a bunch of readers and there are a bunch of writers, but readers do not necessarily need exclusive access to the buffers. Okay? In other words, many readers can be reading from the buffer at the same time because none of them affect each other. If I'm reading data and you're reading data, you reading that data doesn't affect what I see. Okay? The only problem comes in is that when a writer gets involved. If a writer gets involved, we can't be reading while they're writing because we'll have an inconsistent view of the data. Okay? If we get to the exact point where it's writing, right, while we're reading it, we might read one half of a sentence, right, and then the second half of the sentence actually doesn't match up because the writer just wrote something else there or hasn't written enough yet. So we'd have an inconsistent view of the data, which is bad. Okay? So the idea is we need to keep writers exclusively accessing the data, but readers can share access to the data. Okay? As long as no writers are in there. Once a writer gets involved, you need to lock everybody out. Okay? So, what do?
Share with other processes.
What's that?
So when readers can share, that means other processes also could read the process of reading.
Well, they're readers. Other processes that are reading our data are readers in this scenario. Okay? So, we have a lock, this mutex. Okay? We have a write semaphore initialized to 1. And then a read count initialized to 0. And that's just a variable. That's not a semaphore. Okay? But notice these two locks here. Okay? So, now, if you're going to write, you need to seize the write mutex. And that's just normal. We've seen this, right? You wait for it, and then when you're done with it, you signal. Now, the readers do more. What they'll do is they'll get the mutex lock, which is just the regular lock for the data. Okay? Now, what they'll do is when they do that, they're adding themselves as a reader. Okay? And then if the reader count is 1, we'll try and try and seize the write lock. Okay? And then we can signal unlock. What you'll notice about this, wait and signal, right, is this is locking read count. Does everybody see that? Okay? Think of this as like a critical section for read count. We can't just increment read count and check its value without locking it. Why? Why can we not just increment read count without this wait and signal? Right. This is the original problem we looked at. Counter, plus plus. Right? We cannot have multiple processes doing this at the same time. So we lock it. Okay? But inside this locking, we are accounting the write lock. Acquiring the write lock. Okay? Then we signal to unlock it. We do our reading. And then we try to acquire the lock again so we can decrement read count. And then that should be read count again. If it equals 0, we can signal. And then we unlock read count. Okay? So what this does is this is initialized to 1. This makes it so that these readers, okay, they can all get through this, right? The first reader that comes in will acquire the write lock. The last reader that goes out will unlock the write lock. Does that make sense? Okay? Because the writer can't write unless the write lock is unlocked. But the readers can read even if the write lock is locked. Questions? Okay, so the trick is this little piece right here. Right? If it's 1, you're the first one in. Acquire the write lock. You're acquiring the write lock for all the other readers that might be coming in. Okay? Go through. And here, you're saying if you're the last one out, the last reader to read data, unlock the write lock. Because at that point, the writer could come back in. Or more readers could come in. Who knows?
So generally, the wait and signal ideas, can those be kind of thought of as lock and unlock?
Yes.
Wait,
The reason...
Wait is kind of confusing.
Yeah, I mean, think of it like this. Wait for lock. Or wait for mutex. Is that the reason they don't call it lock, unlock is because semaphores can also take on multiple values. So that's the idea. So the idea is kind of wait for one of these to be free. Okay? And then the signal is signal that this is free.
So wait for.
Yeah. And then, signal done with mutex. Is the idea to look at those, to think of those. Okay? This is more kind of the fact that underneath it's, block and signal type of idea. Okay, questions? Any more questions on this? Do you see the benefit of this over the bounded buffer problem? No? Okay, the benefit here is in the reader process. Okay? This mechanism that we're doing here to check if you're the first one in and checking if you're the last one out means that we could have multiple readers come in. If you just have a lock between the two, between the readers and the writers, what you'd have to do is when a reader comes in and it's reading the data, no other readers can participate. And then when it's done, either a reader or writer that's up next can come in, reader write the data. Wait, the next one that comes in, reader write the data. Okay? With this solution, if a reader is in the data, any other number of readers can still come in. The main thing here is that we do not need to lock the data against other readers if only readers are there, because all of them can read without affecting each other. Okay? So this is just a more detailed way of telling the operating system, hey, all of these can go at the same time. None of them will run into mutual exclusion problems. Okay? But none of them can be running when the writer comes in. Okay? The writer is going to come in only one writer at a time. Okay? If we do the mutual exclusion solution, right, the one we saw before, what that's saying is only one process at a time can come in. What this is expressing is one reader or one writer or any number of readers can come in. And this is a common problem. Okay? Think of things like databases, read access to files, all of these different problems. Okay? That happens a lot, and the more that you can let happen at once on this resource, the more efficiency you get from your operating system. Okay? So, reader-writer. Okay? And the final one, we're not going to get too far into. It's more just like kind of a complicated example of how synchronization can be very difficult. Okay? It has multiple processes or philosophers, okay, and multiple resources. Okay? The idea is the premise behind the whole thing is you have philosophers sitting around a table, you have a bowl of rice in the middle that they're all sharing, and then you have chopsticks, okay, that are placed around the table. And the funny thing about these philosophers is they only bring one chopstick each, and they put it next to them. And the idea is that if you can get two of them, you can eat, and then you put them down, and then somebody can use the other ones. Now, the idea is this, is that the reason they're philosophers and not just people eating rice at a table is that sometimes the philosophers are thinking. So, while the philosopher's thinking, they don't need to eat. But occasionally the philosopher gets hungry. So it will go for its chopsticks, and if it can get the chopsticks, it will eat. And now that it's eating, it's not thinking. Okay? So then, when you're done thinking, you put your chopsticks down. Or when you're done eating, you can put them down, start thinking again. So, what is this convoluted example of philosophers sitting at a table? What is that modeling? We're obviously not writing systems for philosophers, right? We're writing operating systems for computers. So, what is this modeling? What are the philosophers? They're processes, right? So, what is a process that's thinking doing? Probably doing CPU stuff type, but it's not really, it's doing CPU stuff that it doesn't depend on any of the other philosophers for. Or it might be waiting, okay? But the idea is that when you're thinking alone and you don't need to interact with anybody else, right? So, the shared the shared resource is what? You might think that it's the chopsticks. It's not the chopsticks. What is the shared resource? The rice in the middle, right? So we want to get at the rice, okay? But how we regulate who can get at the rice is the chopsticks, okay? So here they're showing these chopsticks, 5 of them all initialized to 1, in other words, available, okay? So what you'll do is you'll wait on a chopstick, but you'll also wait on a chopstick next to you. Okay? And then when you're done with them, you'll put them back. Okay? There's a lot more to it. Like, you can't, funnily enough, prevent starvation with this kind of thing. And there's some funny scenarios here. But this is a more complex example. I'm not going to go over it too specifically because it is kind of a convoluted example meant to be convoluted so that you can see that mutexes can solve a lot of problems, or semaphores can solve a lot of problems. Okay? But, I mean, just the interesting thing is this kind of array of semaphores dealing with these mutexes, right? I mean, with these chopsticks, and then you can grab one or the other, and then put them together and do your critical section of eating, unlock them, and then they're available again. And you could be affecting both your right and your left process, right? If you're a circle of processes, you have these semaphores that could affect your right or your left. There's no telling which combination of things is going to happen. Okay? And you'll also notice that 2 processes far enough away can be accessing the rice at the same time. Right? I mean, if you're sitting at a table with this algorithm, okay, this person here can grab their right and left chopstick, right, and eat. And so can this pair, and so can this one. Okay? This one cannot, this one cannot. This one can, this one can. Okay? But if this one does, this other one can. Right? So it's not just 2 out of the 5 can eat. It's 2 specific ones out of the 5 can eat at the same time. It is. I mean, it's basically this conflicting resources between neighbors, and then, different cliques can can do different things. Okay? And you'll see that this is even more of a graph theory problem than it looks, because we'll see that most of this kind of resource dependency thing is done with graph theory when we get to deadlines. Okay? Questions on that? But do you see how kind of all of these things can come together as a complex system, right? We see these fundamental problems of I have buffers that I want to fill up and I want to empty as a consumer. We have this readers and writers. There might be times when multiple people can, multiple processes can work at the same time like this, right? this is kind of a combination of those problems. Okay? But all of it, you really need to get clear about, this idea of what weight means, what signal means, right? We're decrementing the variable here, the semaphore, incrementing here, okay? We can't get through unless we have some of the tickets available, right? So every time you see this, is there a ticket available? There is. I'll take it, I'll move on. I'm done, here's your ticket back. Okay? And you need to see how that mechanism solves these problems of individual processes doing something exclusively. Okay. We're going to talk about these problems more in the next chapter, which is deadlocks. Okay, again, just because an operating system gives you signal and weight, okay, does not mean you cannot write a bad program. Okay? You can still write bad programs by doing the order of the signal and weight wrong, omitting a signal or weight. Okay? Like we saw here, that's a different phenomena than both processes running at the same time. This is synchronizing on these two. So in other words, run this, then run that. When we put these other two pieces here, now it's run simultaneously, but not, try to run at the same time, but not this piece. Okay, not the critical section. You're welcome to finish in either order, but only one of you can be doing the critical section at a time. Okay. And monitors, I debate whether they go over or not. I don't think I am, because we're kind of behind in talking about synchronization. But monitors are an even higher level way of locking, of synchronizing. Okay? The idea, just let me give you the basic gist behind monitors, is monitors are whole objects. Okay? They're a more modern idea in synchronization. They're objects that have methods and variables. Okay, like any objects. Okay? The idea is you put all your different mutually exclusive pieces in the methods of this object. And the object as a whole will ensure that only one process is running methods in the object at a time. Okay? It's not known which methods they're going to be running, but it ensures that only one process will be kind of manipulating the object at a time. So the idea here is that you could put your reading and writing and those different pieces inside these methods, and then have the processes run these methods, and then the object itself will synchronize, making sure that two processes aren't running two different methods at the same time. Does that make sense? The idea is this locking and unlocking, all the methods have a lock and unlock before, at the beginning and end. So, anytime a process comes in and says, hey, object, run this method, it will check. Is anybody else running a method right now? No? I'll run. I might get interrupted or whatever. If I get interrupted, this other process comes in and says, hey, object, can you run this other method for me? They'll say, no, you have to wait because I'm looking at myself and I notice that something else is running a method right now. But I'll queue you up. So then, when we get back to the original process, it finishes running that method. The object says, oh, okay, now I'm free. I can signal one of these other processes that I can run its method. So the idea is to tie everything together in an object rather than all our signals and weights. And the reason that you'd want to do that is to kind of prevent some of these problems of like omitting some of the calls or putting them in the wrong order. It kind of, again, takes a little bit more away from the programmer and ensures that correct use of those methods is always happening. That's the purpose behind all object orientation, right? Is to encapsulate and protect different functionality. So this is kind of objects for multi-programming. Okay, So they have the same types of ideas of weight and signal. All right. So that's it for synchronization. There's a lot to take in there. Okay? Main thing, the basic ideas of locking, semaphores, those different types, that basic Peterson algorithm that we saw, all of them are variations on the same theme. Okay? Locking, unlocking. The fundamental problems, the simple example of the counter variable in the producer-consumer, right? Bounded buffer problem, readers and writers problem. Okay? Fundamental problems, how do we solve them? The idea of a critical section, what that means. Okay? Know that there are these hardware implementations of individual instructions like swap and test and set that can give us, what was the term? Those are special instructions because they do them atomically, right? Atomicity, important. Okay, that's the building block of building all these other more complex locks. Okay, are there instructions I can do without being interrupted? Okay. Okay, and then these are examples. There's one semi-interesting piece in here, but we'll probably talk about that more in the context of file systems. But it's called the idea of transactions and journaling. But I think that's more appropriate for file systems. No questions? On synchro?
No, bro. Just right now, what do you say?
Oh, the synchro chapter. No? It's going to be one of the hardest chapters that.
Can we go a little more on this set and test?
The which one?
Set and test.
Oh, the test and set, the atomic operation?
I understand atomic part, but the code part.
Oh, I'm not that interested in the actual test and set and swap. What I'm interested in is this idea of, hold on, test and set. Okay, the idea is this: it's not doing anything except for it's setting the value to something, right? This variable, right? It's setting it to a value, and then it's returning the old value. In other words, you test the old value, and you can set it to something else. Okay? Why do this? Well, because it's atomic. Okay? In other words, you can do the whole reading of the old value and setting of the new value in one operation. Okay? Why do that? Well, right here. Right? While this lock is true, in other words, you read the old value, right, and try to set it to true, right, while it stays true, you loop. Something else might come in and set it to false. If it does, that means that your old value will be false, so you can break out of the while loop, but then you also set it to true at the same time.
That's where
right? And you set it to true at the same time so that other people trying to get that value, other processes, will still see true. So they'll still loop. Okay? This is a fancier implementation of the same idea we saw before. Notice it's just one statement here, whereas Peterson was all this. And multiple variables. So I'm more interested in that you understand that there are these more complex instructions that are atomic. Okay, and that's important. And it's important because you can use this as a synchronization mechanism. Okay? If you did not have this atomic. If you did not have this special instruction that was handled either by turning off interrupts or a hardware instruction that did it in one clock. Okay, if you did not have that, this code will not work. Why? Because there's the potential that you time slice in between these. And if you time slice in between these, you will get an inconsistent view of the flag, of the lock. And whenever you can see an inconsistent view of the lock, two processes can enter their critical sections. Okay? It's a quick swap. It's grabbing a false out of there so that you can break out of the loop and quickly putting a true there.
And when this code is implementing, what part is it implementing? Because it's swapping the processors, right? Usually that's
Swapping the processors.
the processes. That's what they say.
That's happening all the time. We don't swap the process. The operating system swaps processes from outside. We have no control over it. We have no idea which instruction it's going to do it on. This controls how many processes can be in the critical section. And that's one. Only one can be in here at a time because one will be in it and then it will unlock it. And the next one who sees a false there will break out of their while loop and leave it true. Okay? Again, I'm not as interested in the instructions for test and set, right? I need you to understand that this is another way of doing that critical section problem that we're trying to solve, and this is atomic. Okay? Swap is the same way. It's the idea of taking two values and swap them. This code is key equals true. While key equals true, swap the two. Okay? In other words, you're rotating through two different variables, lock and key. Okay? One of them has to be false. You have to get one of them false so that when it swaps and then comes back into this and we check it, we can break out of the loop. Well, how do we do that? We set it down here. Okay? Using this atomic operation of swap, okay, make sure that we can grab a false value and leave a true value when we get back up there, up to here. So that we can break out, right, and the next one will have a locked value there. Okay? Because the idea here is that both lock and key will be true if somebody's in the critical section. It's not until they get out here that one of them will become false. It'll swap out, leave one of them true, and then come through. That way the next person who's trying to lock will also contribute a true. And again, I mean, these are more complex algorithms for doing the same thing we saw with Peterson's. Okay, but they're all the same idea. I mean, I need to emphasize that. They're all the same idea of doing mutual exclusion. And then we have these more complex, we build that into more complex. Okay? Get familiar with the idea of walking through simultaneous processes and swapping between them. Okay? It's critical to understand that that's all happening outside of the process running. These processes have no control over when they're going to swap or when they're going to, switch over to another process. That's by design. Okay. All right. Let me just introduce deadlocks, and then we'll be done for today. And then Thursday we'll have to go a little bit more quickly through deadlocks. But deadlocks, it's kind of difficult too. But I mean, really, the more we understand the synchronization problems, the more we understand deadlocks. Okay? The difficult part of deadlocks is that there are fancy techniques for trying to not have deadlocks or detect that deadlocks have happened. Okay? We've seen that multiple processes running at the same time, trying to get access to different resources, is difficult. It's a difficult problem that it's hard to visualize them running. Deadlocks are like the most complex form of those problems, that even on code that seems correct and seems to follow all the rules of this locking and unlocking can still create problems. These are kind of problems that can be hard to detect. So let's just look at what deadlocks are. Okay. The first statement here: a set of blocked processes holding a resource and waiting to acquire a resource held by another process in the set. Okay? You have a group of processes. They're all getting resources from the operating system. When we get these resources, we have exclusive access to these resources. Okay? If I'm accessing a disk, accessing a file on the disk, you can't access the file on the disk. If I'm using a printer, you can't use the printer. That kind of stuff. Okay? We have these resources. So, and resources can be as simple as a lock, a semaphore. Okay? If you have access to the semaphore, I can't have access to the semaphore. Right? I have to wait. So, the idea of deadlock is you have a group of processes that some of a process in that group is waiting for a resource that another process in that group has. Likewise, that process is waiting for a resource that process has. You're both waiting for resources that another process has. Okay? Well, if I'm waiting for my coffee, right, and you have my coffee, but you're waiting for my chalk, right, and I have your chalk, and you're not going to release my coffee until you get the chalk, and I'm not going to release the chalk until you release my coffee, we can never go forward, right? I can't go forward to release this resource until you go forward and release that resource, and vice versa. That's a deadlock. Everybody understand that concept, the idea of not being able to go forward. Why is that bad? When will those processes ever get done? Never. They'll never terminate, right? They'll both just be sitting there waiting for a resource. Okay? There's an even worse problem than that. When will my coffee and chalk be free? Never, right? If I can't terminate, I can't release my stuff, I can't release the resources, we'll never terminate, we'll be in memory and all that stuff, we'll have hold of the resources that nobody else can get. Okay? That's a big problem. Okay? So, this example here, okay, is how this happens. We all know the wait call, right? Wait for A, wait for B. Wait for B, wait for A. What do you notice about that? They're flip-flopped, right? Okay? Chances are below this are the signals for releasing those locks. Okay? And the big part here is that you have a signal B somewhere down here. Right? You have a signal B below the wait calls in P0. Okay? And you have P1 waiting for that signal. This guy can't get down to his signal call because the resources that it wants are taken up. So, bridge crossing. The idea of everybody getting to the bridge at once, and they all say, I'm not going to go until the other side's clear. Type of idea. Okay. So, just to kind of give you a heads up on what we're going to talk about on Thursday, we're going to be looking at graphs, okay? We're going to be looking at resource graphs and process graphs. So, The idea is that these processes get access to resources. Okay? An arrow means I'm requesting a resource. An arrow from a process to a resource means I need a resource. I'm waiting for a resource. A resource with an arrow to a process means I'm allocated to that process. In other words, I'm locked. Okay? Once that allocation goes away, that's a signal to unlock. A resource can be assigned to somebody requesting it. Okay? So, things to keep in mind for Thursday. If this looks completely foreign to you, look in the book and try and figure out, read the description of these graphs as to what they represent. The key things when reading a graph, okay, are understand what the nodes represent and what these edges represent. Okay? One thing to be careful for is this is a directed graph. Okay, what's the difference between a directed and undirected graph? Anybody? Arrows. Arrows are the difference between a directed and undirected graph. The reason being is that an edge connecting this node to this node is different if the arrow is pointing towards the process and if the arrow is pointing towards the resource. Okay? This means request. This means assign. Oh, I'm sorry. An arrow pointing towards the circle, okay, means assign. An arrow pointing towards the rectangles means request. I need that resource. Okay? It's directed. Nodes are processes, and nodes are resources. Edges are these requests and assignments. And finally, the other thing is, we're going to be looking for what are called cycles. What's a cycle in a directed graph? It's a loop. Okay? We don't know how many nodes it goes through, but a cycle is you can get from one node back to that node following the directed edges. Okay? So, get familiar with these graphs by looking at your book. We're going to talk about them on Thursday because this is going to be kind of how we look at and understand deadlocks. Okay? Just as a preview, deadlocks are potentially found in cycles of these directed graphs. If you see a cycle, chances are there's a possibility that there's a deadlock there. Even more important is that if there's not a cycle there, you know there's not a deadlock there. Okay.
What happened last time? I suppose like printed out if you wanted. I don't know.
Oh yeah, I'll take it.
I think it went through and something happened last time and it didn't go through.
I think I saw yours. I think it was formatted right.
So okay then.
Yeah.
And one more thing, like you say, you can see your videos online.
Yeah, I ran into some problems. I ran out of disk space on.
But like, I mean, I don't even know how to go there.
Oh, there's a URL on WebCT.
Oh, there it is.
Yeah, and I'm gonna update it once I put the video somewhere else.
Okay. I can draw that kind of chart.
Oh, you have a printout too? Okay, that's fine.
You want me to try from here? Just send it over on the website? Because I have this on the disk beside that guy.
Oh yeah, if you have an electronic copy, you can send me an attachment as well. Whew.
Thank you.